Real gases and its characteristics. So, real gases are non-ideal gases whose molecules occupy space and have interactions. Consequently, they do not adhere to the ideal gas law. To understand the behavior of real gases, the following must be taken into account: compressibility effects, variable specific heat capacity, van der Waals forces, non-equilibrium thermodynamics effects, issues with molecular dissociation and elementary reactions with variable composition. So for most applications, such a detailed analysis is unnecessary and the ideal gas approximation can be used with reasonable accuracy. On the other hand, real gas models have to be used near the condensation points of gases, near critical points, at very high pressures to explain the Thomson effects and in other less usual cases. The deviation from ideality can be described by the compressibility factor Z. Real gases originate from two factors. First, the theory assumes that as pressure increases, the volume of a gas becomes very small and approaches zero. While it does approach a small number, it will not be zero because molecules do occupy space and cannot be compressed. Number two, intermolecular forces do exist in gases. These become increasingly important low temperatures when translational molecular motion slows down, almost to a halt. However, at high temperatures or even normal everyday temperatures, the intermolecular forces are very small and tend to be considered negligible. So for an ideal gas, PV is equal to nRT, or by rewriting the equation, this becomes PV over nRT is equal to 1. The following figure is an example of a plot of PV over nRT versus P pressure for several gases at 200 Kelvin. So for a real gas, PV over nRT approaches 1 only at very low pressures. To better illustrate this, the next figure will show the effect of temperature PV over nRT versus P pressure at different temperatures. So here we have an example of a plot to help us understand the behavior or characteristics of a real gas at different temperatures, and the gas that is used here is nitrogen. And starting first at 200 Kelvin, this is how the curve will look like. As seen here, the curve colored green at 200 Kelvin is too far from the ideal gas, and if we hit this further to 500 Kelvin, the curve will look like this. At 500 Kelvin, observe that the curve colored red seems to be getting closer to the ideal gas. From this we can see that as the temperature goes higher, the curve also gets closer, especially at the low pressure. That's exactly what's going on here. The 1000 Kelvin colored blue curve is a lot closer on the ideal gas law, and this suggests that real gas behaves closely to ideal behavior at low pressures and high temperatures. So to summarize this, for a gas at low pressure, large volume, the volume of the container is very large compared with the volumes of the particles. Thus, at high temperatures, the particles are moving very fast that the effects of interparticle interactions are not very important. Also, the particles are moving at a constant motion, which we will get the gas to behave similarly to an ideal gas. Kinetic theory. In the kinetic theory assumes that all of this space that you see inside the box figure below is available for the molecules to move around it. But in fact, only this amount is available because the rest is taken up by the molecules themselves. So for that, we need to correct the volume on the ideal gas law. Corrected volume. P is equal to nRT over V minus Nb, where Nb, the volume of the particles, N is the number of moles, and B is a constant determined experimentally. Real gases. In real gas, there are some attractions among the particles. Thus, the particles will hit the walls of the container very slightly or less often. And to illustrate this, we have here an example on how these particles. So we have here a particle, and as you can see, the white particle in the center surrounded by colored black particles is traveling outwards, indicated by the arrow. And as shown here, the interactions on the inner particles will cancel each other and the interactions therefore are less effective. However, if we look at the interactions on the particles closer to the container wall, we see that the interactions of particles in front of the container wall are more effective, and therefore the particles will be pulled to the inside of the gas and hitting the container wall less often or with less force. This will then affect the. That's why we need to add a correction factor to the pressure as well, same way with the volume. Corrected volume, P is equal to nRT over V minus Nb, where Nb, the volume of the particle, N is the number of moles, and B is a constant determined experimentally. So here we have the real gas equation, also known as the van der Waals equation. We have here P observed plus A times n over v raised to 2 times v minus nb is equal to nRT, where P observed plus A times n over b raised to 2 is the corrected pressure or P ideal, and V minus Nb is the corrected volume or V ideal. So A and B are called van der Waals constant and they are determined experimentally. They depend on the nature of the gas. Higher molecular weight gases will have larger values of A. Now at low pressure and high volume, the pressure of the gas is greater than the observed pressure of the real gas, and the volume of the ideal gas will be less than the volume of the real gas. To know more about the characteristics of real gases, this another example will let us understand better about the. In this section, we will see some plot that is intended to let us understand more about the characteristics of gases. Okay, now let's proceed with our discussion. So here we have two curves, one is for the ideal gas and the other is for the real gas. And as you can see, there is an intersection between the two curves. This is the threshold between the attractive and the repulsive forces of the real gas due to non-interparticle interactions in ideal gas. At low volume and high pressure, the repulsive force will be greater than the attractive force because particles are forced to come close each other. In this case, if same pressure of both gases is taken, the particles will repel each in reality for real gas, but for an ideal gas, there's no interaction. That's why if particles are repelling each other in real gas, the volume will come out higher than in the ideal gas. And by taking the two volumes, we can see the real volume is greater than the ideal. So for clarification, the green curve here is the real gas and the broken red curve line is the ideal gas. And here by taking the same pressure, the ideal gas particles don't interact with each other. But in real gas, due to its attractive force greater than the repulsive force, particles tend to get closer, making the real volume being smaller than the ideal volume. So we see here that the result is the same because the real volume, which is the colored green curve, is smaller than the ideal volume, which is the colored red broken line curve, meaning the result is the same because they correspond with each other. So that's all for this topic, sir, and I hope you liked the video and thank you for watching.